All right, so let's get started. So our learning objectives for today, we're going to explore how topographic elevation is represented in GPS. We're going to define elevation relative to ellipsoids and geoids, and we'll define these. These are basically different models of the planet's surface, or sea level actually. And then we'll probably take a break because there's a bunch of material to cover there, and then we'll talk about specifics related to RTK GPS surveying. Okay, so question for you guys. What is the shape of our planet? I'll take any guesses.
Round.
It's round. Okay, that's 100% correct. Could anyone try to get more specific? What kind of shape? What kind of round shape?
Sphere.
Okay.
That like bulges out.
Right. So it's not quite a sphere, right? It does bulge, and you know, the bulging is related to a lot of things. One is the fact that it's spinning, right? And so it bulges out a little bit at the equator. Well, let's first talk about how we model a sphere, and you're probably familiar with latitude. Sorry, you're probably familiar with latitude and longitude. So longitude simply refers to where you are in terms of degrees up or below of the equator, and then latitude is across the planet. So if we think about east-west, that's latitude, and longitude is north-south. Of course I get this confused. Okay, so let's start that over. Lines of longitude go north and south, but they tell us where we are in the x direction, so east-west. So longitude will go this way and this way. So you can see these lines of longitude, but they give us our coordinate and relative to this prime meridian, which goes through England right here. So the prime meridian is 0 longitude, and then everything else is either positive or negative relative to that. So latitude is going to be circles that go around from east to west, but they tell us where we are, how far we are above the equator. So latitude is y, longitude is x. Does anyone know approximately what our latitude and longitude is in Colorado? So in Colorado, we are, I'll just draw it. There's Colorado. So we're about 45 degrees latitude. So about halfway between the equator and the North Pole. So the North Pole is 90, and the equator is 0 degrees. And then latitude, so we're actually pretty far. We're 108 approximately degrees latitude away from the UK, which is 0 degrees longitude. So this is called a graticular network, and it just refers to latitude and longitude. So now we use a spherical coordinate system. I said the Earth isn't perfectly spherical, but you know, the coordinate system works pretty well. And you know, here's our degrees. So we're going across the surface of a sphere. So 50 degrees. So we just need 2 points, and then that'll get us our location. So where positions on the globe in the spherical coordinate system are measured by angles relative to the equator and the prime meridian. All right, so those are degrees rather than x, y Cartesian coordinates. So Cartesian coordinates, and we'll talk about later when we get into GIS, Cartesian coordinates are planar, so that means we're just dealing with a flat. If we were to spread the globe out and kind of smush it into a flat surface. All right, so the shape of the Earth is kind of like an ellipsoid. So ellipsis is this shape And then an ellipsoid is when you make this shape, when you spin it around an axis and make it a three-dimensional figure. So that's what an ellipsoid is. So here's our not squished basketball. And when Val takes it to the court and really pounds it on the court there, she makes it squish. So when they're really pounding that basketball, they get an ellipsoid. Here's just the mathematical model of an ellipsoid. There's three parameters that we need to know. The semi-major axis, so that's the longer axis. This goes out across the equator. That's going to be this value A, and then B is the vertical axis, the semi-minor axis. So A and B are not going to be equal to each other. If they were, we'd have a sphere. And then you can calculate this flattening parameter F, which is a function of A and B. For the Earth, this is the model, the spheroid that we fit to the planet. And A is equal to, let's see here, 6,378,000 meters. And then you can see that it is a little smaller, not a lot, 6,356,000. So that difference there is what makes it a spheroid, and it's not a big difference. We're talking about 20,000 meters right there. So 20 kilometers difference along the A axis versus the B axis. And the way we measured these values was from ground surveys and satellites. So GPS benchmarks allowed us to measure what these actual A and B values are. So these numbers actually didn't come out until 1984 after we launched the first GPS system. So we're going to talk about different kinds of datums. Datum is, we talk about datums as a reference point. When hydraulics, we talked about the datum as being kind of like the zero value, and we evaluate water surface elevations relative to that datum. In GIS and GPS systems, datums provide a frame of reference for measuring locations on the surface of the Earth. So X, Y, and Z. So we have horizontal datums, which give us a frame of reference for X and Y. And then we have a vertical datum, which gives us reference to Z values. And so we need to know the origin and orientation for latitude and longitude lines. So we have a horizontal datum that is this ellipsoid, which is the blue shape here. All right, so there's a lot of different kinds of datums, and we're going to kind of be using these words a lot, so we're just introducing them now. A local datum aligns the spheroid or ellipsoid to fit the Earth's surface for a particular area. And so in this case, you can see this red dashed line right here. And this is called a local datum because, say, this is North America right here, North America. We want to have it fit so that it's really accurate and close to the surface of the Earth where we care about. And so if we care about the North America, we're going to have a datum maybe that we'll use that fits North America. And so that's one that's called North American Datum, NAD 27. 27 refers to 1927 when it was first created, so it's pretty old. And because it fits North America decently well, it really doesn't perform well. You can see it's really far away from the Earth's surface, if represented by this black line, in other parts of the world. So the coordinate system origin of a local datum is not at the center of the Earth, and it's not fit for, as you can see right here, it's not the center of the Earth. It's not fit for the whole globe. It's only fit for a local part of the area. But we now use, if you turn on your GPS and get a lat long value, it's going to be called the WGS 84 datum. And what that is an ellipsoid that's been fit to our planet to represent the mean surface elevation, or mean sea level elevation. And that is centered on the Earth. So it's like within 2 centimeters of the center, of the actual center of the Earth. And so that's a global datum. or Earth-centered datum, also called global. And that's accurate, relatively accurate everywhere on the planet. So it's not just fit for like North America, for example. So I talked about the NAD 27. It's what's used on old USGS topo maps. It's based on 26,000 surveyed benchmarks across the planet. Here's one for Mount Bierstadt, if anyone's climbed it. You can see that in 1955. You've got an elevation on there. Is there an elevation? Do they stamp it? No, sometimes they stamp the elevation on there. Does anyone know? Has anyone been up Bierstadt? Probably not going to know off the top of your head. It's a 14er, so it's about 14,000 something feet. And that elevation is going to be within this old framework. So the framework's been updated. There's the North American Datum, 1983. You're going to see this a lot with GPS surveying. It's the most current datum for North America. It's based on 250,000 benchmarks, as well as satellite data. It's Earth-centered. It's almost 2 meters off. And it moves as the continent moves. So they're updating it continuously because the continents actually move, and we need to update the ground relative to the planet. Now, the last datum I'll talk about right now is called WGS 84, World Geodetic System 84. It's the standard coordinate system for GIS. Like I said, anytime you go on Google Maps, turn on your phone, you get some coordinates. It's going to be, the lat long is going to be relative to this datum. And it's actually 2 centimeters off of Earth center. So it's the most accurate we have for the lat long coordinate system. So we note that the NAD 83 is always updated. I think 2011 was the most recent. And so they're correcting it based off of this system of GPS stations. And we'll talk about the core system in a little bit, but these are ground-based systems that talk with GPS and track the movement of the Earth over time. So continuously operating reference station cores, they're all across our country. This is what they look like. There's several in Mesa County. Maybe we'll go out and get to see one. And they're permanent stations that monitor the location of the Earth. So let's talk a little bit more about WGS 84. There's a lot contained in it. So here's the ellipsoid. It's fit to sea level. Here's the values for the semi-minor axis, semi-major axis, and then the flattening value. It's a smooth model, right? It's a spheroid or an ellipsoid. So it's very smooth, representing mean sea level, because we want to know our elevation relative to sea level. That's kind of our reference. And then when you turn on your GPS and you get an elevation, it's going to give you the ellipsoid height. I'm going to talk about what that is. It's basically your height above this ellipsoid. Okay, so planet Earth is a funny shape. And this is an exaggerated shape, right? It's not actually this bumpy, but it is lumpy, right? It's not perfect. We got mountains. The sea level isn't the same everywhere, and it's awkward, right? So a sphere is this, and then we have WGS 84, which is an ellipsoid, and it tries to fit the surface of the Earth as best as we can. And maybe if we think of the lumps as actually the undulations in the sea surface, we know that sometimes the ellipsoid is going to be below the sea surface, and sometimes it might be above the sea surface. And then when you're actually on the surface of the planet and you get your GPS point, it's telling you how far are you above this ellipsoid, which models the sea surface. So when we want to think about ellipsoid height, it's simply if the ellipsoid is fit to represent the ocean, it's our height above that kind of mathematical model, that simplistic model of the Earth's surface. But mean sea level is a really complicated thing. It's not just a perfect, smooth surface, and it's lumpy. The winds, the currents can make it lumpy. gravitational anomalies. So where we have denser bedrock, the sea surface could be higher or lower depending on that. So denser bedrock would would attract the sea surface down and make it kind of a valley, and valleys in the sea surface actually make bubbles or ridges in the or the seabed make ridges in the sea surface. So what does the real sea surface look like? Well, it's approximately an ellipsoid, but it's only a model. And in fact, if we want to get a more accurate representation of sea level in a vertical datum, then we need to go to a geoid. And this is a more complicated version of the mean sea level. Okay, so now we're adding a layer here. The green is going to be our ellipsoid right here. And this is that kind of smooth surface that supposedly represents the sea surface. And in some areas it matches up, in some areas it doesn't. Because the Earth has different sea surface levels across it, in order to get the most accurate estimation of where we are on the surface of the Earth, what the elevation of this ground is, if we want to get our survey, or we want to know an accurate estimate of the ground, we need to actually turn to a more complicated model called the geoid. And the geoid is basically, it's just a raster, a series of grid cells that tell you how far above or below the sea surface would be relative to the ellipsoid. And so in this case, where we are right here, the geoid is below the ellipsoid, so it would have a negative value. And then here's our ellipsoid height, so this tells us how far above the ellipsoid we are. And then ultimately, the most accurate estimate of our elevation on a surface of the land relative to sea level is called the orthometric height. So this is what we ultimately want to calculate. This is called the orthometric height. So where there is a surplus of mass, and on average, the geoid surface is going to be above the ellipsoid, and where there's a deficit of mass, the surface is going to be below the ellipsoid. All right, and so when we go to the conterminous US, the geoid height is typically below the ellipsoid, so it's negative. But if you go to Alaska, it's actually going to be positive. So let's look at this another way. The ellipsoid is going to be in black, and then the geoid is going to be in green. And in some cases, the geoid falls below the ellipsoid. In some cases, it goes above the ellipsoid. And remember, the geoid is going to be this estimate, the best estimate we have of what sea level actually is. And so the geoids are always being updated. Our current geoid is called 12B for the US. Geoid heights can be positive or negative. And each country, there's a global geoid, and there's also kind of like a continental geoid. And so for the US, this continental geoid is that we typically use is called 12B. And it's just been updated. I think that was in 2012. Okay, so this is a really extreme look at what our sea surface looks like in the planet if we were to kind of really exaggerate it. And you can see that we've got some dips here where there's maybe extra mass, and then some elevated areas where there's less mass. So that this is kind of what the global geoid actually looks like. And here it is in the US. So you can see that it's really negative up here in the Yellowstone area, and then it's less negative in the Yellowstone area, and then it's more negative as we get into other parts of the country. So all this means is that it's complicated, right? It's contours. Each little point is going to have a different value, and so this is just kind of like a raster model that we can sample. And then we have the ellipsoid, which is, so these are all basically values that are negative or relative to the ellipsoid. So if we want to do a calculation, we take our GPS unit, and it tells us, say, that our ellipsoid height is, we'll just keep it simple, 1,000 meters. We know our geoid height in the US, say in Colorado, it's negative 14 meters. If we want to calculate our actual height, so h is going to be our orthometric height. We say h is equal to our ellipsoid height, so 1,000 meters, minus our geoid height, minus 14 meters. And that is going to give us our actual height, so that would be 86 meters. This is going to be our orthometric height, and this is going to be our most accurate representation of the elevation of the Earth's surface, where we are relative to what mean sea level would look like if the ocean could travel underneath our continent. Okay, so we talked about datums and horizontal datum. So the North American datum 83, this is what gives us our X and Y horizontal frame of reference. The WGS 84 is also a datum that we use for latitude and longitude. But we also need to know, we need a vertical datum. And that vertical datum in the US is called the North American Vertical Datum 88, NAVD 88. This is the datum that allows us to say, okay, what is our 0 meters mean sea level? What actually is that? So this is another system that we need to talk about. All right, so we have the North American datum, which is X and Y. And then we have the North American vertical datum, 88. And so it is the surface of equal gravity potential to which orthometric heights, remember orthometric is what we want to calculate, that's our best estimate of the elevation of the Earth's surface. And so this is the definition. It's 6.271 meters along the plumb line, so vertically, below the geodetic mark at Father Point, Remenowski. And I'll show you where this is. So this is a geodetic survey, like a benchmark. It's actually not in the US, it's just across the border in Canada. And we said mean sea level is just 6 meters below this benchmark. That's what we said. So it's arbitrary, but it's what it is. And so from that point, from that vertical measurements off of this benchmark, we have over 500,000 we have over 500,000 vertical. I'll get back to it. Hang on, guys. There we go. 500,000 geodetic marks across North America that have orthometric heights that we've surveyed in, all relative to this one point. It's kind of crazy. So let's look at that. Here's that survey. Here's this network. And so whenever these lines come together, we have a geodetic benchmark. And then you can imagine, here's that Father's Point right there up in Canada. That's where we said mean sea level is 6.2 meters below that point. And then we have this whole network relative to that one point for the whole system. Okay, so just to show you, when we update our benchmarks and add more data, which happens continuously every so many decades, how sea level changes. So these are the steps of the Colorado Capitol building. And originally, the University of Denver survey crews, they had their engineering department in 1909. They said 1 mile, 5,280 feet above sea level is right here on this step. Well, then CSU came back in 1969 with an updated benchmark system and said, nope, 5,280 is right here. And then finally in 2003, we had the Professional Land Surveyors of Metro State and the CDOT, Department of Transportation. We've got a lot more benchmarks that have happened in the last 50 years. And they said, here's 5,280 right here. So it's changing, right? And these are feet of difference, and feet of difference is really important. So a survey from 60 years ago is not going to be accurate in terms of elevation as compared to a survey from modern times. All right, so let's review. Orthometric elevation is what we want to calculate. for elevation. It's based off of this North American vertical datum. And when we go in to calculate it from GPS equipment, we get an ellipsoid height from the GPS. How high are we above from that smooth, you know, mathematical model of mean surface elevation of the ocean? We subtract out the geoid height, which takes into account gravity and how gravity affects mean surface elevation. And then we calculate ultimately our orthometric height, which is all relative to that benchmark, that North American vertical datum. So, but you have to know the geoid, and geoids change. And so if I have a GPS survey from 5 years ago, it might be based off of geoid 12A. 12B is what's programmed into our GPS units. 18 is out there. It's not been widely used yet, but it's another geoid that's available. And so here's just another cartoon. Here's our base station. Here's our benchmark that we have our base station set up on. And here's how we get to that orthometric height. Okay, so we have geometric or horizontal datums. And again, these are ellipsoid models of the Earth. WGS 84, NAD 1983, this is for North America. This one is for the whole globe. When we do surveys, will be our horizontal datum. Unless we're using a projection, which we'll talk about later, which is a flat system. When we're just using straight GPS, this is what we use. And then we have a vertical datum, vertical reference based on mean sea level. And that's our vertical datum, North America vertical datum 88. And then, you know, you guys probably won't have to deal with this, but if you do have an old GPS with an old geoid, then here's the equation to actually update your geoid. So if we want to get our new orthometric height, we have our old orthometric height minus the new geoid value plus the old geoid value, and that's how you would update that. And you can do that with software that we have. And here's a website that'll actually help you calculate that. Okay, well, we'll take a break right there. I need a water break, and I'll see if there's any questions about all that. Okay, let's see if we can summarize that. I'll start at the bottom. Tom, can you tell me what what a horizontal datum is, and give me an example of that?
I guess that would be like the equator. Is that a horizontal datum?
That's part of the datum, right? So yeah, the equator is the zero value for what's measurement.
For latitude.
Yeah, so it's 0 degrees latitude, right? Are there any songs that talk about latitude? I feel like there's a Jimmy Buffett song that's talking about he wants to be in the right latitude with a good attitude. Anybody? I'll come up. I gotta find that. Not a parrot head myself, but we'll find that. Okay, so horizontal datums or geometric datums represent the surface, right? So we have x, y, lat, long. And when we're talking about spheroids, we have these coordinate system, right? The latitude, longitude, degrees, minutes, seconds coordinate system. Okay, Christian, how about a vertical datum? How do you define a vertical datum, and what are the parts of it?
I would be dealing with elevation, correct? Like how you were talking about here in Colorado, we're 14 meters beneath the sea level. So with mountains and hills and all that stuff, that's how we calculate the elevation that we're at.
Yeah, exactly. And so the datum is the 0 value, which you said is mean sea level. Kalisha, how do we estimate mean sea level? What's one way we can come up with a way to say this is what mean sea level is for the whole planet?
So we represent the mean sea level with the ellipsoid, and we have kind of calculated based off of the mass of different areas of the Earth, how that affects where the mean sea level would be.
Right, so the ellipsoid is kind of the real simple version, and we say, okay, we're gonna fit this ellipsoid, this smooth shape to the planet, and it's really close, at least to the center, but maybe sometimes it's above mean sea level, maybe sometimes it's below mean sea level because we have all these gravitational anomalies, currents, that sort of thing. So what you were talking about, the fact that it's not always fitting it, Val, what do we use to most accurately represent mean sea level across the globe?
I don't remember.
Okay, so I'll give you a hint. It's called Geoid.
Oh yeah.
And can you tell me why the mean sea level might not be a perfect smooth ellipsoid?
Cause like I don't know, in the like picture you showed, it's like not always the same height, but I don't know why.
Okay, and it's kind of a complicated thing to understand, but the idea is the Earth is not, the gravity on our planet is not the same everywhere. So that's a kind of a hard concept to wrap your head around. So if I'm walking on the Rocky Mountains, gravity is going to be different than if I'm walking on the plains of eastern Colorado. And it's not necessarily because I'm farther away from the planet, it's because there's more dense rock in the Rocky Mountains, and that dense rock has more mass to it, and that greater mass has greater gravity. And so that plays out because of the geology across our planet. And where you have more mass, you are okay. It takes me a while to figure this out in my brain. Where you have more mass, so water can move, right? Water can go from Bermuda across to Africa or whatever, right? Water can travel, and so it's attracted to more mass. So where we have more mass, water tends to pile up. So let me go back to that picture. Here we go. Okay, so if we look at this red, this is a pile of water. The water surface elevation is greater than this kind of ellipsoid. And the reason is because we have more gravity, you're actually you're pulling more water to that point. And so you get like a ridge or a mountain of water, essentially, a mound of water. Where you have less gravity, the water isn't as attracted. So it goes away from that area towards the areas of higher gravity. So you can kind of think of it as like a mini, not a black hole, but like if you were to put a black hole in the ocean, all the water would be attracted to that and it would kind of mound up over that. I don't know if that makes any sense, but that's worth a shot. So that's why we have those undulations. It's kind of hard to wrap your head around. And so at the end of the day, what are we interested in calculating, Tom? What's the elevation that we want to know? That's the most accurate representation of the ground surface elevation.
I think it's the orthometric height.
Orthometric height, yeah. And this orthometric height, we calculate it based off of two things. One is our, let me just go back to full screen here. Okay, so one is our ellipsoid height. And if you guys pull out your phones, does anyone have a phone with a GPS app on it? I'll just do mine right now. If you've got a GPS app on your phone, pull it out and open it up and find your coordinates. So I'm going to do that right now. I've got my GPS logger. I'm going to open it up and start logging. So it says, oh, I gave you guys the wrong latitude. So we're at 39 degrees latitude and negative 108 longitude. What elevation? Anyone get an elevation? If anyone's get an elevation, just holler it out and we can talk about it. So I'll just show you mine. So this is GPS logger app. I think it's backwards. I should change that.
I have 4,606 feet.
Okay, great. Does that seem high or low? Where are you? Where are you on top of the National Monument?
No, I'm just in the valley. It seems high.
Yeah, it's a little high. I think. Well, I'm over in Redlands. I've got 1,393 meters. So we'll see what that is in feet real quick. We can just kind of compare how accurate we are. Who can tell me why your vertical estimation from GPS units is not as good as your horizontal?
Because the signal can't get through the Earth, so you only have you have a smaller angle for the satellites.
Yeah, you don't have a 360 coverage of satellites in the vertical realm as you do. You do have 360 degrees around you for satellites in the horizontal realm. Yeah, I got 4,575 feet. So that elevation is our ellipsoid height right here. So these coordinates, the XYZ values that you see here, lat long and elevation, are the WGS 84 system based off of this ellipsoid. Now, if I wanted to calculate, you can actually, some apps will do this now. You can have the geoid loaded into it, and the geoid is just going to be basically a grid cell. So every point in North America is going to have this n value in it. And so it'll say, okay, you're in this grid cell, you're 14 meters below or whatever. So you can actually get an orthometric height that's like, I don't know, with a phone. Right now it's telling me that I've got an accuracy of 10.7 meters. So, take it or leave it, but you could correct it based off of the geoid height to get your orthometric height. So if I were on a boat and I had my little GPS unit here, the boat's at sea level, right? I'm cruising around, say it's a sailboat, so I'm like right at sea level. I'm cruising around. Say I got a negative value, value from my ellipsoid height. What would that mean, Christian, if I got a negative value at the surface of the ocean?
That would mean that at that point that you're at is underneath the
ellipsoid.
Yeah.
Yeah, exactly. So there I have maybe a low gravity. So maybe there's a big, San Andreas fault or something, and there's not a lot of mass there. And so the ocean's going to dip away. Maybe I'm out here in the ocean, and here's my little boat. That kind of looks like a house. Let's try that. There we go. Here's my boat. And so I'm actually underneath the ellipsoid. That's kind of crazy. That's okay, but that's what's probably going on. It could also be that you're on a mound of water and you're above the ellipsoid. That could happen too. Okay, those are the major concepts I wanted to introduce to you guys. I guess the last point I'll make about WGS 84 is that it's the actual, it's a lot of things, okay? It's actually the ellipsoid, so it's that, you know, semi-major, semi-minor axis values right here, the A, B, and F. So it's that model of the globe that's 2 centimeters off from this actual true center of the Earth. It's this coordinate system, right? Latitude, longitude. And it's which is part of the horizontal datum, and it's also that vertical datum. So it's actually 4 things. It's your GPS coordinate system, it's the horizontal and vertical datum, and it's an ellipsoid, and it's the standard GPS system for the whole globe.